Okay, let's get started. Today we're going to talk about techniques for characterizing nanostructures. And before we start, I just want to ask how many people here plan to take the GCC exam, the Mechanical Engineering GCC exam? Raise your hands high so I can have a count. 1, 2, 3, 4, 5, 6, 7. Okay. And as a reminder, there's no class next Monday because of the MLK holiday, so our next lecture will be on Wednesday, January 20th. So a quick recap of what we talked about last time. We talked about ways of naming and visualizing and thinking about nanoscale structures. I think it's the first topic as we try to build sort of a set of tools that we can use to understand the properties of nanostructures and then how nanostructures interact and how to make them and put them together. So our first topic was the taxonomy or classification and naming of what I'm going to refer to as our building blocks. And I feel that an important concept here is the idea of the number of dimensions of the structure we're dealing with. And this is a terminology that's used a lot in the field. And it's not the same as what we would think as like 2D and 3D in terms of pictures. But imagine yourself inside a little box that's in the nanostructure and think of how many degrees of translational freedom you would have if you're stuck inside of there. And the idea is that if you're in a little nanoparticle, it's so small you have basically 0 degrees of freedom. If you're in something long and narrow like a nanowire or a nanotube, you have 1 degree of freedom. And if you're in a sheet, such as like a sheet of clay or a sheet of graphene, you have 2 degrees of freedom because you can move laterally. And that's going to relate directly to what we're going to talk about as governing the properties and the confinement of energy carriers when we pick up on that topic next Wednesday. And another point of emphasis here was the kind of structural diversity we see. Not only is the crystal structure important, and remember there are these 14 basic crystal structures for all materials, but we also see effects of size and shape because of this coupling between the dimensions and the properties. And the second topic was this, both kind of abstract mathematical yet also very real idea of magic numbers, or numbers of atoms that represent geometrically closed shells. And perhaps the simplest geometric case is the cubic lattice here, where you have to have a cube with flat sides or rectangular prism with flat sides. You have a certain number of atoms, and basically you destroy that symmetry or that closeness of the shell if you add 1 or subtract 1. And we saw how these are actually observed, and this was a schematic from these experiments with titanium nitride where they saw peaks at each of these magic number clusters corresponding exactly to the numbers here. And we also know that C60 is an example of a magic number cluster. And then third, we talked about the structure of carbon nanotubes, specifically single-wall nanotubes, as an example that we'll build upon in terms of what I'll call structure-property relationships, or how minute changes in the organization of the atoms at the nanoscale can equal pretty significant changes in the properties of the structures. And we saw that there's this specific notion for each single-wall nanotube, which is based on mapping the hexagonal lattice of the graphene sheet to the tubular arrangement of the nanotube. So we played this rolling game and defined a vector, the circumferential vector, C sub h, which goes around the waist of the nanotube and connects one lattice point to the other lattice point. And by the number of steps, n and m, we take in each of the unit vector directions a1 and a2, we can uniquely specify that structure. And we stopped basically on this picture, which is this so-called periodic table of carbon nanotubes, not necessarily the same as the periodic table of elements we know, but it was put together by this company that does a lot of, develops software for computations of atomic structure. And what I want to emphasize here is that you have so many possibilities for these different N-M combinations leading to different types of nanotubes. And changing one atom step in either direction, in that A1 direction or A2 direction, equals another nanotube. And as we'll learn later, and as color-coded here, the pink represent nanotubes that, due to their structure, how the structure relates to the properties, are metallic. So they behave like metals in terms of their electrical properties. And the sort of gray or tan-colored ones are semiconducting, meaning they have a finite band gap. So sort of this one atom change, say going from, let's say, a 6,6 to a 7,6 tube, can go from metallic to semiconducting. And this relates to a lot of interesting thought about properties and also thought about synthesis. How could you, for example, control the synthesis of nanotubes to get only these instead of these, where the size difference is basically 1 atom in circumference, which is really, really small. And we'll talk about that later. It's sort of one of the emerging yet still unsolved problems in control of the synthesis of nanostructures like this. And you do have hundreds of chiralities in a diameter range of 1 to 3 nanometers. And the chart also calculates all these structural parameters for the nanotubes, and the derivation of some of these is described in the reading that we had from last time. So that was just a quick summary of last lecture's topic. Before we move on, I just want to pose a question. Can anyone speculate as to what the smallest carbon nanotube might be? Say in terms of diameter or number of atoms across, and then maybe why that would be the smallest nanotube. Does anyone have a guess?
12 atoms.
12 atoms? So why 12 atoms?
2 layers of 6 atoms each, like 2 hexagonal rings.
So you're thinking the rings side by side, or like?
In parallel.
Okay. So you're counting around the rings. Okay. Is there another? I'm not saying that's incorrect, but I want to hear if there's another thought.
Only with a diameter of 6 carbon atoms would be the smallest.
Okay. So, well, it turns out that the smallest nanotubes, I guess you don't necessarily have the hexagonal ring, around from the top, but it's pretty close to that. I guess you get into the definition of when do you start to break down the idea of rolling up a sheet. But what governs the stability of the smallest nanotube is the fact that you are introducing so much strain into the lattice to wrap it that it becomes highly unstable. And those answers of about 12 atoms or about 1 ring turn out to be correct, close to correct, not necessarily because of that exact ring, but because you're distorting what wants to be a planar structure so much. And these are experiments where researchers have grown really small nanotubes, for example, they're so unstable that they have to confine the growth in very small pores of ceramics, or confine the growth inside larger nanotubes. So this was one paper that showed a 4 angstrom diameter tube, and this one showed a 3 angstrom diameter tube, and this is the structure. And as you can see down to this, you get sort of the idea of the nanotube goes away, and they believe it's actually sort of 2 strips of hexagons with bonds connecting them, where it looks kind of flattened. But there is, when you get to really small, you then end up distorting things so much that you can actually limit the size of the structures, and beyond something like this, you might end up just getting a chain of atoms and having atoms bond to the sides.
Produced, and are they stable in long aspect?
So they're going to be very easily degraded by air if you have defects in them. I don't know, specifically how long they will last, but not only will they be easily degraded if they're this small, but they'll also be, in ambient, but they'll also be easily degraded in the growth atmosphere, which is often more volatile because it contains some hydrogen, which can easily eat away at carbon that's not in the best state. Okay. And there are things like software. This is just a link to a cool program you can download if you wanted to build some 3D models of nanotubes. Okay, so today's agenda is really an overview of techniques for characterizing materials at the nanoscale, and focusing mainly on structural characterization by microscopy, and we'll talk a bit about optical microscopy, electron microscopy, and scanning probe microscopy, using 3 different modes to interrogate what's down there at the nanoscale. And then we'll talk a little bit about surface and structural analysis using electrons and X-rays, and a bit about optical spectroscopy. I really feel like I need to say that this lecture could be an entire course, and the emphasis here is not to know the details of all the methods, but really to give an overview of the basics of the different methods that are most frequently used to characterize nanostructures, because as we go through the other topics, we're going to be looking at a lot of pictures and spectra using these techniques, and we want to have a working knowledge of what it means. If you end up being more interested in one of these techniques, then you can certainly go and read about it. We're not going to focus a lot on the mechanism of characterization characterization, as we are going to focus on the use of the characterization as a tool to enable understanding of the properties and processes that we want to learn about. And I feel like characterization is in many ways what enables discovery and enables now nanoscale science and engineering and technology. Because if you look at some of the things that we saw on the first day, like nanostructures being in old glass windows, or scientists in the late 1800s growing carbon nanomaterials, perhaps if they had the electron microscopes we have today, they would know what we do today back then. But it's the ability to look and understand at the fine scale that lets us then iterate. And so innovations in characterization are also very vital to innovations in manufacturing. And I have two readings up on CTools. The first one, I think, is just a nice paper because it's the first paper about the atomic force microscope that we'll learn about today. That ended up winning a Nobel Prize for the co-authors. And then I have a review paper on characterization of nanomaterials by physical methods. So it's just a description of some of the characterization techniques we're going to talk about today. You'll find that it has a paragraph on this and a paragraph on that and a picture of this and a picture of that, and it's largely incomplete, but I just provided it to be a bit more information about what we're discussing. And I also have some extra readings, and this is really based on your own interest. They're pretty deep and in new directions, but those are just a flavor of what the forefront is in the case of these techniques. Things like, we'll talk, a lot of the techniques we'll talk about today are essentially static, or you could say pretty slow. It takes maybe a few seconds to get an image or a few minutes to get an image because you need to scan slowly. Well, a lot of the forefront is now using, building upon these techniques to get very high rate dynamics. So using, for example, very fast pulses of X-rays or light or electrons to characterize, transport, and take pictures and do things like watch electrons or watch photons move through materials, and or take three-dimensional images of very small volumes. And some of those papers, of the extra papers, talk about that. But I leave that more so just based on your interest. And in terms of additional resources, instead of sort of the background I talked about last time, I think just look into the references on these slides, search the internet, look at review papers. There are a lot of good books that review characterization methods, such as the one that's listed here. And there are also a couple of courses at Michigan if you wanted to learn more about material characterization. This one, I think, is an advanced undergrad course in the material science department. It's offered this semester and probably pretty frequently. And then Professor Daly in mechanical engineering offered a course on experimental methods in solids. This was done last year, and I'm not sure when she's going to offer it again, but I'm sure if you're interested, you could contact her and ask. So let's start thinking about these different characterization techniques, and by showing our calibration ruler again, I want to emphasize that conventional optical microscopy, which was the state of the art until the, say, early to mid-1900s, puts us at a limit of, say, a few hundred nanometers. However, a lot of the things we're interested in looking at the nanoscale are way smaller than that, so we need to devise new techniques to understand and observe these structures. And I've cut the length scale bar in half here and put up this plot that shows approximately the progression over history in the resolution of characterization techniques we have to look at materials. And the resolution units here are in inverse angstroms, so angstroms to the -1. So this is 1 angstrom or 0.1 nanometers. And then because you have 10,000 angstroms in a micron, this is 1 micron. And so you see that up until about 1920, the world was working on optical microscopy, and then we saturated it a fraction of a micron. And then the electron microscope was invented, and even still now are we advancing the resolution of electron microscopes, and now by means of correcting the imperfections in electron images by understanding how the images form and how you can perfectly use magnetic fields to focus electrons, we can go even higher. So now we are approaching or realizing imaging techniques that have the resolution of single atoms, and in some cases even pushing to subatomic resolution. But it's taken a long time, and you can see that our advances in resolution are decreasing, but we are getting to the ultimate scales. And you could say that, well, now we can only go so far in terms of physical space, so now we want to go into time space. But I think this has very much pushed what we've been able to do. So let me ask you, if you want to look at a nanotube or a nanowire or a nanoparticle, what types of information do you want to get? What do you want to measure, or what do you want to know? Just shout out ideas.
Diameter.
Diameter, so length scale, size, what else?
Bonding.
Someone said bonding?
Yeah, bonding.
Okay, so what do you mean by bonding?
How not just where the atoms are, but how they're bonded together.
Okay.
It's covalent or whatever.
Okay, so what atoms are bonded to what? That's totally right. Something else.
Conductivity.
Conductivity. Okay. So some physical properties.
Strength.
Structure. Yeah. So the bonding and also the crystal structure, the organization of the atoms.
Strength.
Strength. Mechanical properties.
Surface chemistry.
Surface chemistry. Okay.
Thermal properties.
Thermal properties. Optical properties. All right. So all these things. So we want to know as much as we want to know, and not only do we want to know the size, but we want to know the placement of the atoms, and we want to know how those, you could say, physical or structural attributes relate to the functional properties of the material. And this lets us to get to things like maps that try to approximately put different characterization techniques in a space. And so this is my attempt at adapting information that I found and trying to map out the spatial resolution, or the finest feature that you could measure, with the amount of chemical information that we get from a technique. Basically, what the atoms are, in addition to the fact that they have a certain size, and how they're bonded and so on. So you see optical microscopy is about a micron, electron microscopy and scanning probe microscopy, which we'll talk about, push the resolution to about a nanometer. And then if we use other means of interrogating the structures using, say, X-ray beams or using light, we can get a whole lot more chemical information. We can even resolve chemical information down to the molecular scale or down to the molecular level of information. So the difference between those two, I mean, like molecular scale would mean I know what molecule is in what place. Molecular level would mean that that you have something which is made out of a whole bunch of the same molecules, and I have enough of it to be able to say, oh, I have carbon bonded to nitrogen, for example. And a lot of optical techniques that, for example, simply excite the material with light that causes it to vibrate mechanically, and then measures, then uses, say, scattered or emitted light to measure the frequency of that vibration, are a very useful and practical and robust way to identify those bonding configurations. And if you know the frequency, the vibration frequency of a certain bond, because you know its strength, it's like having a spring and two masses, and that is practically how a lot of that information is obtained, if you have enough molecules or of those bonds in your material to make it happen. And so these maps are not always inclusive, but there are often a lot of trade-offs. And if you're characterizing a material, you want to use a bunch of different techniques and know what different techniques can get you to get the information you want. So our trajectory today is going to sort of start at optical microscopy and go down to finer and finer resolution microscopy, and then we're going to talk about X-rays, and then we're going to talk about optical spectroscopy. So you've all seen simple sort of benchtop optical microscope, something that you might have in a basic high school science lab. And the idea here, so we can build upon it, is just you have a beam of light and you use optics to focus that light, and you use optics to collect that light, and how you introduce the light on the sample and how you design the system to magnify the image determines the resolution of your technique. The ultimate resolution is say a fraction of a micron in the case of conventional optics. But in all of the techniques we're going to talk about, the difference is just going to be we're going to have maybe a different type of excitation, and we're going to have a different type of measurement. And the fundamental characteristics of that excitation and measurement are going to determine the resolution of the technique and the type of information we're going to get. But when we look at the limit of why can't we see features beyond, say a few hundred nanometers using a conventional light microscope, it's by the diffraction limit, or the fact that you can't measure things that are generally smaller than the wavelength of light. And there are many modifications to that statement, but simply the spatial resolution is defined by this little equation up here, that the minimum distance you can measure is the wavelength divided by the numerical aperture of the lens. So by changing the characteristics of the lens, you can, for example, slightly beat the limit, and that's used in advanced lithography, for example, to slightly push this limit down. And another way to look at it is that the ability to, say, differentiate between two points. Imagine that you have 2 points emitting light, sort of at ideal delta functions. They will have a function of emission that looks like that, called an area function, and the ability to measure the distance or resolve the location of those 2 points is sort of the minimum distance that you can measure. And I'm showing you this also because there are a lot of interesting ways that people are trying to use optical microscopes to overcome this limit, or to sort of change things a bit so you get more information with sophisticated techniques or with knowledge of the situation. So if, for example, you use special optics that increase that numerical aperture, or to some extent what should be in your image, like what shape of the features are generally going to be, or for example, something about the texture, then you can use that extra information to, say, interpolate between things you can measure using an optical microscope. And then another thing that can be done is if you can, say, attach light-emitting molecules, fluorescent tags, or quantum dots, like the semiconducting particles we saw in the vials before, and we'll talk about later, you can then, put essentially little light bulbs at specific locations, and you can effectively illuminate features that are smaller than what you could see in the first place. And that is a very widely used technique that we'll see more about when we talk about optical properties. And for example, there, if you can use chemistry to, say, attach these fluorescent molecules or fluorescent nanostructures to certain areas of tissue, say certain antibodies or certain proteins expressed on cells, then you can get these sort of striking, colorful images that might have higher resolution than you could get if you didn't use this technique, and they also might give you additional information. For example, if you know that you've designed your green particle to attach to one type of surface and your blue particle to attach to another type of surface, then you can not only get an idea of what's there, or where one thing is versus the other, but what it is versus the other thing that you're interested in. But for that, I guess you need to have some extra information to improve the situation. And one other technique that's been invented in the past 5 years or so, there are a bunch of these approaches, but I think this one has been particularly impactful and interesting, and this is called STORM, and STORM stands for Stochastic Optical Reconstruction Microscopy. And following the figure up here, which is all this is developed by the Zhang group at Harvard. They have a lot of information and papers on their website. They designed a fluorescent molecule that is photo-switchable. And what this means is they can expose, so it means you take a sample. So say you have a piece of brain tissue that has this complex network of neurons and axons and dendrites where the feature sizes are smaller than the wavelength of light. They can coat this tissue with this molecule, and the molecule is designed chemically to respond differently to 2 wavelengths of light. So if they hit it with red light, then the interaction between the red light and the molecule causes it to turn on its emission behavior. Basically, then if they hit it with green light, because they've hit it with red light first, then it's going to glow. And then they can hit it with red light again, and they can turn it on again, and then red light again, and turn it on again, and so on. And what I didn't say just a second ago is if you do that in different areas of the tissue, or hit it with that red light, so you only turn on a part of the emitting molecules at a time, you can basically take several pictures where the distance between your light bulbs is bigger than the diffraction limit, but if it's all stable, you can then overlap those images and you can get a picture that's way beneath the original limitation of the system. So it's worked incredibly well, and this has really enabled a lot of interesting observations and discoveries. So this is an example of a piece of brain tissue, and this at the same length scale is a conventional image that's gained if you just look at this fluorescence emission under a regular high-end optical microscope, and this is the image that you get with this technique because you can put together the results from all these images from very widely spaced small points. And I don't know the details, but they're working on a three-dimensional method of now being able to sort of scan by focusing into the depth of the tissue, and this might, for example, decouple information that would be sort of pressed into the two-dimensional plane to go into the network. So one of the goals here is to be able to get three-dimensional optical images of things like cells and tissue, and this is something that would be very difficult or impossible to do in electron microscopy, because we'll see that for electron microscopy you need a sample that's electrically conductive, and tissue isn't electrically conductive, which means that you'll burn it, you'll dry it out in the vacuum environment, or you'll have to coat it, for example, with metal if you wanted to image the surface, and that can clearly destroy the types of information that you might want to see. So the next step down in the length scale of looking at materials is to use an electron microscope. And still the storm technique and the other advanced optical techniques don't have the resolution of an electron microscope because an electron microscope can go down to, you could say, the nanometer length scale, dictated in the same way as optical microscopy by the wavelength of the beam, but the wavelength of electrons and X-rays, as we see later, is much, much smaller than light. So therefore, you can resolve smaller features. So as we saw on the history plot, the resolution of electron microscopy or electron microscopy has been around for decades, but it's been consistently getting better and better. However, the principle has always remained the same, and that's that instead of having a light source, a light bulb, you have an electron source, which is typically a filament of metal that emits electrons. So imagine a sharp tip, a very sharp wire that is heated very hot. So when certain materials get very hot, they undergo what's called thermionic emission, and they emit electrons. And if you have that in an electric field, you can sort of strip off a beam of electrons. There are various designs for these emitters, but you want to create a very nice and sharp and stable beam of electrons. And then you need to focus it. So you send this beam of electrons down a column, and instead of having glass lenses, you have electron lenses, which are magnets. And so by controlling a magnetic field around this beam, you can focus the beam and you can move the beam. And so you have these lenses, and you have coils that you have currents running through, and that lets you place the beam on your sample where you want. So you take your substrate or your whatever you want to image, and you put it in the microscope, and then the microscope creates a picture by scanning the electron beam across the surface. And then through a bunch of electronics, which in addition to innovations in the emission and the optics have let the resolution increase over time, you get an image, and you can control the scan speed versus the quality and so on, and you end up say looking at the surface here, and I don't know what this is exactly, but it looks like, for example, some pollen spores or some diatom-like structures. And here's a picture of a typical scanning electron microscope, an SEM. So up here, we have the electron emitter, and this is the column with the optics and the scanning coils. And your sample typically sits in this chamber, and you can see it's on this little post here. And this is big and husky because it operates in vacuum. You couldn't get such accuracy with an electron beam if you had it in air, because air would scatter the electrons. So there is a constraint of the technique in that your sample has to be vacuum compatible. There are variations on this that let you, for example, use a little bit of moisture or seal your sample in very, very small, you could say, little boxes. But by and large, what you put in an electron microscope has to be vacuum compatible, so it can't be wet and so on. And also the sample has to be electrically conductive because that electron beam that scans across the sample is going to charge your sample, and you need to have a means of dissipating that charge to maintain a stable imaging condition. So if you have something that's a polymer sample, you can image it using an electron microscope, but you need to coat it with metal, and that can affect the resolution you can achieve if you need to, for example, coat it with a metal that's tens of nanometers thick, and then you won't be able to see features that are smaller than that. And there are many manufacturers of electron microscopes. I just put this slide in to sort of give a flavor of one of the main manufacturers is the Japan Electron Optics company. And when they say tungsten, I think they mean that they're using a tungsten filament. And actually, the choice of filament and the design has a big impact on the characteristics of the image and the limits you may maintain. And in this case, this was a couple years ago, they were reporting the point-to-point resolution of their microscopes was 3 nanometers. So you're about a factor of 100 beneath a diffraction-limited optical microscope. And that translates into a magnification of about 300,000. And on the previous slide where we saw this post, this is typically on a motorized stage that you can move around and tilt, so you can really kind of get a 3-dimensional picture of the environment you're looking at. So here's an SEM picture of an array of patterned vertically aligned carbon nanotubes. So we'll see how these grow later, but here we've used optical lithography to pattern a catalyst, which then we put in a hydrocarbon atmosphere, and the nanotubes grow up, kind of like little buildings. And I feel like one of the important things to note about scanning electron microscopy is how the interaction between the electron beam and the sample creates kind of lighting effect. So it looks to me, in some ways like there's sort of spotlights over here, but it's totally dark in there, and light wouldn't make a difference. It's the way the electrons interact with the sample that cause these kinds of shadows. And because the sample is, you could say the electron beam is sort of scanning over this back and forth, because the sample is thinner over here, it looks lighter than it does over here where it's thicker. And if, for example, this weren't electrically conductive, the carbon nanotubes are electrically conductive, the picture would very quickly blur out and disappear. And that's where you would need to coat it with a conducting material to make the imaging technique work. And so this is a fairly low resolution image using an SEM. You could take an image with this magnification, 50x, using an optical microscope, but you wouldn't have the type of resolution of the texture and also the depth of field. And I think, to me, that's also one of the useful aspects of an SEM is that you get a fairly large depth of field. Everything in here, to a certain extent, looks pretty much in focus, although this is tilted at about 45 degrees and we're looking deep across it. And it was expressed on the previous slide with the specifications. We can go down to nanometers, and this is a picture of the forest as you zoom in. I made this little dot, which is still way larger than the dot would be in reality. Maybe the dot is way less than 1 pixel on the screen here, but then you can zoom in and you would start to see the organization of the structures, and we are still far from the atomic level here. If each one of these is a carbon nanotube, which is maybe 10 nanometers in diameter, there's a lot of information which we can capture. And that's sort of the limit of the SEM. You could make this, maybe this picture 5 times more magnified, but with a scanning microscope, we're not going to see the atomic organization. We're going to see that with a TM, as we'll talk about in just a moment. So I've probably mentioned a bunch of these details already. If we're preparing a sample for SEM, you want an electrically conductive surface, and you typically put it on the stage. The stage is the post that we saw in the chamber with a conductive tape or a conductive adhesive, because even if your sample is conductive, you need to mount it to the machine, and that needs to be electrically conductive. And if you need to coat your samples with a thin layer, you typically use one of these chambers, which is a vacuum deposition machine. So it, for example, has a little piece of gold in it, and it heats that gold very hot to thermally evaporate it, and this is in vacuum, and then you'll deposit a thin layer of gold on your sample, and that'll render the surface conductive. Or you can use what I alluded to before, a technique called environmental SEM, which puts a little bit of vapor, for example, water vapor, into the chamber, and the goal of that water vapor is to de-ionize the surface or enable imaging of non-conductive samples. But that relates to a direct sacrifice in the resolution because of how the vapor affects the technique. But it also enables some interesting in situ imaging, for example, looking at condensation of droplets on surfaces and so on. And that's certainly a topic that you can read more about if you're interested, or if you want to ask for references, I can point you to a few papers that talk about environmental SEM. So another thing, in this sort of whirlwind review of these characterization techniques, I want to emphasize is that there is some overlap between techniques for characterization at the nanoscale and techniques for fabrication at the nanoscale. So as we move on through the lectures, we'll bring in some examples from fine beam lithography. For example, using beams of electrons or beams of X-rays instead of beams of light to play with materials and to fabricate them. And in the same vein as electrons have a finer wavelength and enable finer resolution than light, electron beam lithography can be a higher resolution technique than optical lithography. And I just think this paper is a pretty cool and appropriate example. But in this paper, the authors used a standard SEM chamber and used the electron beam in the SEM chamber to pattern a thin layer of ice and to use that to then use lithography to create very narrow features. So it's maybe nothing more than a cool prototyping process, but this is a cross-section of their sample inside the SEM, and so their sample was sitting on a cryo stage, or a stage that keeps the temperature very low. And what they did is, because this temperature, the substrate is very cold, they brought in a little spray of water vapor, a little spritz of water vapor into the chamber, and the vapor froze on the surface of the substrate to create a thin layer of ice. And then they used the fact that if they hit this thin ice layer with an electron beam, the electron beam will heat or ablate, blow away some of the material to create a little groove in the ice. And then they exposed this sample to a metal deposition environment. So in fact, they had two machines hooked together so they could create this little groove in the ice and then move the substrate over into the metal deposition chamber. And then they put a thin layer of metal on top. And then they basically melted the ice. So if the ice is under the metal is going to go away. And they created this thin line. So this sort of a novel way to put a couple technologies together. But another point here is that the interaction between these beams and materials can also change the situation and can be used for some aspects of fabrication. And this would be an example of what I'd call a top-down fabrication, taking something existing and cutting it into pieces. And if, for example, you could then create the line using this technique and maybe assemble some nanostructures along that line, that would be a combination of a top-down and a bottom-up technique. And we'll build upon that idea as we move on. Okay, are there any questions about SEM or the previous example? All right, so now if we step down to another level of resolution, really approaching atomic resolution, if you don't see what you want to see in the SEM, if your sample is good for the SEM, it can typically be modified to use a TEM or a transmission electron microscope. And the difference in terms of the interaction with the material between TEM and SEM is, in a TEM, you're shooting the electron beam through the material and basically casting a shadow of the material when it's illuminated with the electron beam. And so now you have the same idea. You have an electron source emitting a beam of electrons, and you have a bunch of optics and apertures that let you do what you want with the beam to focus it down onto your sample. And you have, in this case, optics both before your specimen and after your specimen, and then by operating those in the right way, you then collect an image on a screen far down the column. And in the past, even I'd say 5 or so years ago, when I started using TEMs in grad school, the TEMs still had film. So you'd have to go and insert the film and expose the image and then take it out and develop it. And now most TEMs have CCDs, so you can take images a lot more quickly. But you're actually putting electrons onto a screen and taking a picture of the electrons that are scattered, or you could say cast away by the nanoscale structure that you're holding. So you put an individual tube in the TEM and you hit it with electrons and you see how they interact, and that's how you generate your picture. So this, for example, TEM was what was used almost 20 years ago to first show the structure of single-walled and multi-walled nanotubes, and now you can imagine that the electron column that was horizontal in the previous image is coming down like this, and we're hitting our suspended carbon nanotube with a TEM, and we're taking pictures that give shadows that show the individual walls or the individual layers. So our single-walled tube here is casting an image like that, and at cross-section it looks like that. And so here's a picture of a typical TEM. All TEMs generally have this kind of vertical column design like an SEM does. And this is just, I took the previous image and rotated it to give you the idea of how the electron beam passes through the specimen and how the CCD or the film detector is typically down here. And when you're operating one of these instruments, this is a picture of a different one, you can sit at the station, you can sit at the desk and you can see your image on the screen and you can drive it with the controls, but you can also operate in a mode where you actually look and you see the electron image of your structure on this phosphor screen, and then you can sort of take this screen away and you can let the image go down to the detector. And I mean, certainly you can imagine that the sample that you would put in one of these microscopes is super, super small, and this is a sophisticated and sort of challenging imaging technique, but the preparation of the sample is also pretty challenging. You can imagine for an SEM, I mean, you need to prepare your sample and get it on the post and put it in. It has to be conductive and anchored and so on, but to get a good image in TEM, you need to have your sample consisting of the nanostructures you want basically suspended over a hole and thin enough such that the electron beam can get through it. So you typically do this on what's called a TEM grid, and typical TEM grids are 3 millimeters in diameter, so that's already pretty small. But what you need to put in there is much smaller and across a little gap, as we'll see in a minute. But this grid goes into what's called a sample holder, which is like this post like so. And then you put your grid onto the tip of the sample holder, and you pick it up and you install it up here in the middle of the column. And that sample specimen location it correlates with the position of the specimen up here. So the beam comes down, hits your grid, which is held inside the electron beam, the beam going right through here, and then brings the image down for adjustment and collection. And similar to the SEMs, just specifications from Joel, and the emphasis here is that clearly you can see that you can get resolutions of a fraction of a nanometer down to 1 angstrom, and much, much higher magnifications resulting from the higher resolution. I should have said before that the accelerating voltage is basically the voltage that's applied between your sample and the electron emission, and this has relations to the resolution you get and the type of microscope and so on. So if you have learned or will learn electron microscopy in the future, you'll know that there are a lot of things you can adjust, such as this accelerating voltage and the current that the beam represents, and that can very practically determine, for example, whether you have a better image of the surface or whether the beam is driving a bit down into the surface and getting you more of an image of the bulk. I mean, the bulk is not like going far into it, but whether you're just touching the surface with the beam or you're penetrating the surface by, say, 10 nanometers or so can make a big difference in the way your image looks, and also can let you see what you want to see. And here's another TEM image of an individual nanotube. It's a multi-wall nanotube, about 10-15 nanometers in diameter. And in analogous way as those researchers use the SEM electron beam to pattern the ice, if you have your electron beam sitting on your material for too long, you can also damage it. And some people have used this to cut things or to join things because the electrons are hitting the atoms of your material and essentially knocking them out of place. But in this case, this image was just taken by having the microscope beam sit on this nanotube for 180 seconds or 3 minutes, and you can see that you can severely damage the structure. And this is just in this case, it's meant as a practical consideration to show how there are interactions between these beams and the material of interest, and this can certainly affect the suitability of imaging of the structure you're going to take. If this were, for example, not this fairly large-sized 15 nanometer tube and it were one of these 3 or 4 angstrom tubes, this could be so unstable that you may not even see it. It may be gone before you see it, and I think that perhaps, I don't know the details, but getting that image, that electron microscope image, the TM image of the little nanotube we saw, was probably a pretty excellent feat in TM expertise in itself. And to connect to the example of zinc oxide that we showed last time, this is just some excellent characterization of the structure of these helical belts from Z.L. Wang's group at Georgia Tech. And here they were using TEM at high resolution, at the resolution that will resolve the lattice, to show that these belts consisted of different domains having different crystal structures. So I don't recall what crystal structures these are, but you see this striping from one domain to the other, and you can actually resolve the atomic interface, and you can see that the orientation of the lattice is different, and they suggest that it's that in the synthesis process, whatever drives that change or the formation of that domain boundary is what then causes the twist, because these bands then stack up into having you could say a sub-micron scale twist resulting from this atomic interface behavior. And another thing you can do in the TEM is you can do electron diffraction, or you can take a diffraction image that lets you compute the crystal structure based on the position of the diffraction spots or diffraction peaks. And we'll talk more about that later, but in the TEM you can typically switch it into a diffraction mode and you take a picture, but this picture removes certain apertures and optics from the column, so you're able to just impinge the beam onto your sample and therefore collect a diffraction pattern like so. And here are some higher magnification pictures of TEM grids. So the little, this is, for example, copper grid that goes in the sample post that goes in the column. And there are many different types of designs of grids or membranes based on what you want to image. If you have, say, a dispersion of nanoparticles or nanotubes that you want to suspend over a hole, you're going to get the ideal image if you have your structure suspended over nothing. So if I can make my individual silicon nanowire carbon nanotube so it is hanging over a gap with nothing in the background, then I'm only going to interact the electron beam with what I want. If, for example, it's too small to be suspended or too fragile, I could, for example, put it on a very, very, very thin film, like a very, very thin plate. And then I'm going to sacrifice some resolution because of the interaction with the beam and that film or plate, but I'm going to be able to image it. So this is a case, this is an example of a copper grid, you could say with, say, 20 micron pitch here, and then one that has a lithographically fabricated polymer film with a whole bunch of organized small holes. And this is an example of a microfabricated silicon TEM grid where anisotropic etching was used to expose a very, very thin silicon nitride membrane. And this is like a solid plate of silicon nitride, and these come in oxide and so on. And that would be, for example, you could deposit some particles on there, and you could, for example, heat them before you put them in TEM, and then you could put that in the TEM. So there are companies that sell a lot of these, and the sample preparation depends what you exactly want to do. And there are also techniques that are used to carve up things to put them in the TEM or to make them suitable for this electron transmission imaging. Basically taking what you have and making it thin enough so you can see it in the TEM. Because if it's thicker than, in practice, say 100 nanometers or so, or a few hundred nanometers, the electron beam is not going to go through it and you're not going to take an image. And the thinner your sample is and the more suspended it is, the better your resolution is going to be and the better the image is going to be. So one way that other types of samples are prepared, say you have something that's like a little block that you see in the SEM, and you can't necessarily put it in a liquid and shake it up and throw it on the grid. Say you want to look specifically at one place and take a little slice and then shoot the electron beam through that slice. Now it's really hard to do that, but it's possible if you can essentially machine the material at the nanoscale. And one way that's done is using a FIB, or it stands for a focused ion beam. And this model just schematically shows the idea of hitting your material with a high energy beam of ions and throwing atoms you don't want to away. So it's kind of like ionic nanoscale water jet. And so here's an example of taking say you have a silicon substrate with a little patch of something that you're interested in, and you want to look at a cross-section of it. And so you might, for example, take your focused ion beam and machine a little cutout here, and then you could machine another cutout here, and then you would have a sample that you could orient vertically in the TEM, and although this would be very hard, it's certainly possible, and then you could look through it. And if you could get this to be tens of nanometers in cross-section, you would have a nice image. I don't have a picture of a focused ion beam here, but it's you can imagine it essentially as an SEM, as a vacuum chamber that can take a picture while you have another beam coming in that lets you machine things away. So you can watch the SEM image and you can drive the fib, and you basically see material disappearing before your eyes as you cut it away using the ion beam. It's not a perfectly clean process. All these atoms also result in junk, so you get some small scale junk in the process as well. And so here's a picture of a sample that was actually, this is a multi-layer circuit structure that was machined by fib, basically cut out to reveal this thin 300 nanometer section, which was then put in the TEM and had an image taken. So I guess in this case, the researchers wanted to look at the characteristics of this thin film and, for example, see its grain size and grain structure, and you wouldn't be able to see it in an SEM because it's buried, and also the resolution will be limited. So quite a painstaking process, but it can certainly work, and that's the type of thing that you would do to thin out an existing sample. So, as with optics for optical microscopes, the design of the optics and the understanding of the optics in the electron world are also important. And that is one of the things that determines the true resolution limit, and that's what's letting us climb that last part of the curve up to what the graph called corrected TEM. So the real details aren't important here, but basically the approach is to create techniques and algorithms that understand and correct for the aberrations in focusing the electron beam. And an aberration is when the beam, instead of all the rays being focused at one point, a result of an aberration is the rays being focused at different points, and that gives you a distorted image. And basically, it's really hard to eliminate these aberrations in metallic lenses, which in practice means it's hard to get a perfectly focused electron beam by having a perfectly designed magnetic field. And also the diffraction of the electrons at the apertures. You often use an aperture or a pinhole in the microscope to basically only let the center of the beam through. Diffraction from those cause aberrations as well. So by understanding this and developing software to correct for it based on the CCD image, it's now possible to take these very, very high resolution pictures of materials and, for example, image the placement of atoms and individual defects. And it's also more difficult to do this for atoms that have lower atomic numbers or lower, you could say, lower atomic weights, because an electron beam of a certain energy that may be more effective at imaging will be more likely damage a more fragile or lower atomic weight material. So you need to have a better image at a lower accelerating voltage, for example, to image something like carbon, whereas you might be able to use a higher voltage or a higher current or a higher beam intensity to have something like zinc oxide or a metal. And so these images just show here they're taking a high-resolution picture of an individual carbon nanotube and trying to pinpoint the placement of the individual atoms in the hexagonal lattice. And this doesn't look so exactly like a hexagonal lattice because of the way the tube is maintained, but basically what they've done here is they've mapped out what they show is a defect in the structure, and here they showed the existence of this so-called Stone-Wales defect, where you have, instead of 4 hexagons, you have 2 pentagons and 2 heptagons, and we'll see another flavor of that when we start talking about mechanical properties next week. And so this is really letting us finally perhaps relate atomic structure to electrical properties, and if it were possible to, say, take this 1 nanotube and hook a couple of wires to it and measure its electrical transport, one of, you could say, the ultimate visions is to be able to map out the positions of all the atoms and then be able to relate that to the properties of the structure while you're taking pictures of what's going on. So there's certainly effort toward that end. And relating to this idea of hooking things to wires and taking other types of measurements while you're taking pictures, there's also a lot of research on doing other things while you're taking images in an electron microscope. And like environmental SEM, there's also environmental TEM. And this is also quite a sophisticated technique, but I just wanted to show you one example of this where researchers want to view dynamic processes inside a TEM. And so what they've done is sort of a step beyond the idea of having your sample on a simple grid. They've built a simple cell where you could, for example, fill this cell with liquid, and if you have your liquid very, very thin, that is held between two very, very thin membranes, then you can, for example, do something inside this little cell or little box at atmospheric pressure and keep the rest of the stuff all at vacuum, and you can pass an electron beam through these windows and start to take a picture. And this was from a few years ago, and they're more sophisticated, or you could say, neat-looking designs since then. But by connecting a couple of silicon wafers with thin windows in them and a couple of electrodes, sort of by a combination of manual assembly and microfabrication, they created this little cell which they put on their sample holder in the TEM and ended up passing the beam straight through this window like there. And we're able to see. The goal here was to observe the electrode deposition or electrochemical growth of copper nanocrystals. So they had a solution of copper salt in here, and they were applying a voltage between these two plates, I believe. And they, on one of the surfaces, got deposition of these crystals and were able to see the growth of them. And the capabilities of these techniques have now been refined, and this is sort of just a proof of a concept of the type of technique you might be able to use to combine, an imaging technique with a process of interest. And there's also work in, say, looking at carbon nanotube growth and looking at, say, materials diffusing and merging or assembling, and you'll find a wealth of literature on topics like this. And you could say this is sort of another one of those forefront areas where, rather than statics, we start to look at dynamics and we start to look at the real processes as they go. And another important thing to me here is that, in principle, you would seek to replicate, for example, the same process in this little box with the electron camera as you would if you had, say, a large vat and you wanted to produce a large quantity of these materials. So these techniques can indeed lead to a lot of insights that are relevant for larger scale fabrication. Okay, are there any questions on TEM? So the next imaging technique we'll talk about is scanning probe microscopy. And this can have a lot of flavors, but the two main flavors are STM, or scanning tunneling microscopy, and AFM, or atomic force microscopy. And both of them schematically look the same in that you have, the principle is you have a very, very sharp tip, like a very small fingertip or a very sharp pencil. And based on interactions between that tip and your substrate, you create an image. And the difference between STM and AFM is how you create that image. But in both cases, the overarching principle is that if you can create a tip that has atomic sharpness, one atom at the tip, and you can understand how that one atom or how the bunch of atoms at the tip interact with your substrate, you can create an image of truly ultimate resolution. And there are examples that are quite close to that. So the STM is first because it was sort of invented before AFM, and AFM was kind of a derivative that overcomes some of the limitations of STM. So in STM, you have your sharp tip and you have your substrate, and if your substrate is electrically conductive and your tip is electrically conductive, you can apply an electrical signal, apply a voltage between the tip and the substrate. And if you have a very sharp tip that is above your substrate by a very small gap, then you can use a behavior known as electron tunneling to measure the distance between the tip and the substrate. And in fact, at these small distances, say 10 to 100 nanometers, there's an exponential relationship that is well known between the current, the tunneling current, or the number of electrons that jump across here at a fixed voltage at a certain distance. So how STM operates is you have your tip and you have a motion system and you have feedback electronics, and you move the tip over the substrate to, for example, maintain a constant tunneling current, and you monitor the displacement. Or, for example, you could keep the position or the gap the same and you could monitor the tunneling current, and knowing that relationship you could create a height map of your surface. And typically the gap is maybe 1 nanometer to 10 nanometers, and you're using this relationship to measure the displacement, and you end up with an image. And certainly there's a lot of physics behind this, for example, how you control the current or how you control the position of the tip. But if you ideally had a tip that was 1 atom sharp, this effect is so confined that you can make the assumption that most of the current is going between the sharpest point of the tip and your sample, and you could say even more of the current is going in a slightly larger zone. And so certainly here you want to have the sharpest tip possible and the smoothest substrate possible, but it's actually possible if you made a very, very sharp metal wire, for example, you broke it down by applying a very strong current through the wire, and you used off-the-shelf components, you can actually build a sort of benchtop STM that does reasonably well. And the STM was used to make this image that we'll start to see next time when we learn about why this image looks like so, but to map the electron density of a ring of atoms that were placed on a metal substrate. And remember, here we're seeing the existence of one real atom, and here we're seeing the reflection of the electron waves that are emitted by this atom because they interact with the sort of fence of electron density that's around it. So that might sound a bit vague now, but we'll start to see next time why this picture exists and how it's made, and it's kind of an analogy to confining the energy levels in a small space. The energies that are allowed for the electrons of this atom are influenced by the electrons of the other atoms that are in proximity of that. And this was taken by an STM, which was able to map out the local electron density around these atoms. And you can see that the density is highest at the nucleus, and it decays off as you get farther away from the nucleus. And that's why all these peaks look like that. And the image was certainly, color was added afterwards to emphasize the different levels and contrast, but this is what it really does look like. Okay, so the analogous technique to STM is atomic force microscopy, or I should have put AFM up there. And here you have the same idea of a sharp tip and a substrate, and you want your tip to be as sharp as you need it to be, but instead of using electrical interactions or this electrical tunneling current where you need to have the tip and sample conductive, now you are relying on physical interactions between the tip and the substrate. And this is the topic of the paper that I have in the readings folder for today. And so here you actually physically scan your tip over the surface. And you can scan it in various modes. You can actually drag it, or you can sort of bounce it in what's called tapping mode. And the ability to do that is built into these instruments and is well known. But here you measure the position of the cantilever with respect to the substrate by, say, reflecting a laser off the top of the cantilever and collecting the reflected signal on a photodiode. So you can imagine that if this is like a little compliant diving board, if this bounces up and down as you move your sample side to side or up and down, the position of this reflected spot on this detector will change, and you'll therefore be able to get an idea of how much the tip is moving. And it's also typical, for example, to calibrate the stiffness of these cantilevers. And if you know the stiffness of the cantilever and you know the displacement, then you can know the force. So you can also use AFM for a lot of nanomechanical characterization. And the fine attributes of AFM get into the actual molecular interactions between the tip and the substrate. And for example, if you bring your sharp tip close to a substrate, if in some cases you get, say, within a couple nanometers, because of the van der Waals forces or the intermolecular attraction between the tip and the substrate, as we'll learn about in a few lectures, the tip might actually get pulled down and contact the surface. Likewise, if you then try to push harder, then you may then you can't go any farther. You might get a repulsive force. So those interactions and how those interactions vary with different materials are important to getting really pushing the limits of this technique. But in principle, the way the instrument works is you just scan your tip across the surface, and you can take different types of images that you can with an electron microscope. Typically, a strength of AFM over an electron microscope is that, well, now AFMs operate in atmospheric pressure, so you don't need the sample to be in vacuum, and they also don't require conductivity. So AFM has been, you could say, most valuable for imaging things like biological samples or polymer samples that might not be conducive to imaging in an electron microscope. Another advantage of AFM is that you can measure topography, so you can get really three-dimensional profiles of a surface. And in an SEM, even if I have a really good picture of the surface, I may not have a good idea of how tall, say, an object is. So if I have my little pencil and I scan it up above a step, and then that step is 1 nanometer high, I can actually measure that height with fairly reasonable certainty. And that's another thing that I might do with an AFM as opposed to an electron microscope. And here there's a nice gallery of images from a lab in Germany that does research on AFM, and this is one that I think really pushes the limits. But here they're using a very, very sharp AFM tips to take topographical images of graphite, and here you're actually seeing the hexagonal lattice. So you're seeing these being individual atoms, and this is distinctly an AFM image rather than an STM image. So this is based on physical topography rather than electrical interactions between the tip and the sample. So as you can imagine, to get images with such high resolution, the design and fabrication of the tips is very important, because it is the shape and the characteristics of the tip that determine the type of picture you can take. At one limit, if you are, imagine you're an AFM, if you're taking an image with your fist, you're not going to have nearly as high a resolution as if you're taking the image with your pinky finger. And if you're, if you have, for example, a groove in your sample that's, say this big, my fist is not going to fit in, but my pinky finger is going to fit in. And so there's a lot of technology to microfabricate these sharp tips using silicon wafer fabrication and growth and etching, and also adding things such as nanowires or nanotubes to the tips of these cantilevers. And this is an idea where if you have a very, very sharp and high aspect ratio tip, although it's in practice quite fragile, you can then image physically very, very intricate features. And that reduces what's known as the convolution between the tip and the sample, in that, kind of the same idea I was trying to show you over there with my fist and the hole through the nanotube model. If I have a fat and wide tip and I want to use the AFM to measure the topography of these microstructures, this plot is showing a comparison between the image that's obtained if I just have this pyramid tip versus a tip that has a long, narrow nanotube on the surface. And this is done as a comparison because you can see what the section really looks like in SEM, and you can see what it looks like in AFM. And here, if you use the normal tip, you see the walls appear slanted because you have the slanted surface of the tip interacting with a straight wall, and you can imagine the tip kind of rides up over the wall and the signal looks crooked. However, if you have a nice straight tip, then you can get a much more accurate profile of the surface. And although this is an example really at the microscale for comparison, the same thing would apply to nanoscale features. If you had a whole or an array of nanoparticles that were spaced like so, and your tip didn't fit in between the nanoparticles, then this tip would tell you the substrate is flat, whereas this tip would tell you you have the particles like so. So in practice, things like choosing the type of tip are important for selection of what you want to image. And there are other examples that I'll jump over in the interest of time, but there are also, in the mechanical sense, there's a lot of work on, for example, measuring the mechanical properties of individual molecules by AFM, and that has relevance to biology and understanding forces involved in self-assembly as well. And another sort of frontier topic is increasing the rate of AFM by mechanical design of the system and understanding of these tip-sample interactions and dynamics to, for example, start to be able to take pictures of things like viruses moving on surfaces. Or I'll pull up a video quickly from a lab in Japan that is a video of a little kinesin motor moving along a microtubule. I don't know what the length scale is, but this is probably on the order of tens of nanometers. And if you can take these pictures very quickly and you've designed your technique so it doesn't poke everything too hard, you can start to image things that couldn't be imaged in an electron microscope and likely couldn't be imaged by those high-resolution optical techniques, because that storm technique needs to sort of flash the light off many, many times. So this is an area where, while basic AFM is still doing quite well, where there is still a lot of research in the limits of these techniques for Okay. So we have like 9 minutes to go, and I have a lot left to do. So I don't think we're going to get through everything, but we'll do what we can. Are there any questions now?
Is it possible for the tip to damage the sample, or was it?
Sorry, to what?
Is it possible for the tip to damage the
To damage the sample?
Yeah, or
certainly.
was it?
And the tip can break, or the tip can, the cantilever can break, but more frequently the tip can snap off or get something stuck on it, and you may notice your image getting bad, and it could mean the tip has gone bad. Like if you have a whole bunch of nanoparticles on the surface, then one might not be well stuck, and you could pick up a particle and it might be hanging out on the tip and going for a ride, and then you might need to change the tip and start imaging again. Okay, so the next topic is getting into ways of quantitatively determining the structure of materials using X-rays. And this schematic shows a generic process for using an X-ray beam, which is like, in some ways like an electron beam, to do what's called X-ray scattering or X-ray diffraction and create a representation of your material in 3 dimensions. And this technique goes very, very far, for example, to understanding the crystal structure of proteins by biologists, as well as understanding, at a more simple level, understanding, say, whether you have an FCC material or a BCC material if you're looking at a bulk metal or a nanoparticle inside an electron microscope. But the general idea is that because it can be mathematically determined how a beam of X-rays or a beam of electrons interacts when the atoms in a material are in certain places, then we can take a diffraction pattern or a scattering pattern of a sample, and then we can do some math on it to calculate what organization of atoms we actually have. And there are a few manifestations of this in practice, and one of them is called X-ray scattering, and X-ray scattering and diffraction are used somewhat synonymously, and typically the way I like to see it is when people talk about X-ray diffraction, they talk about the material experiencing an electron beam and diffracting the X-ray beam at a fairly wide angle, say, tens of degrees. And when people talk about X-ray scattering, they talk about the same process, but having the scattering or diffraction happen at fairly small angles. And the basic thing I want us to grab here is that we can understand certain things about the material by impinging it with a beam of X-rays, where for this you have an X-ray source and you have a set of optics and slits that create a collimated small X-ray beam, and then you pass the beam through your sample, and then based on those interactions, the X-rays get scattered or diffracted, and then at some way down you have a detector and you take an image. And this, for example, shows an X-ray diffraction image from a particular crystal. And in this case, we have, if you have rings, we'll see in a minute that you can look at the position of these rings to determine the lattice spacing within your material. If you had a single crystal, basically one block that's a whole cube of atoms perfectly organized, you would see dots in the X-ray diffraction or scattering pattern. And if you have a polycrystal, so you have a whole bunch of little cubes all in different orientations, then you will get rings in your pattern. And the typical way that the structure determination is done in this case of a crystal is you take your diffraction image and then take a line scan of the intensity out from the center, and then you look at the position of these peaks, and you can use the position of the peaks along with a model of the crystal structure you expect to calculate the parameters of interest. And you can have different types of X-ray sources, and the type of material you can characterize, the size of sample that's needed, and for example, how long it takes to collect the data basically depends on the intensity of your X-ray source. So there are sort of benchtop or room size X-ray diffraction instruments. There are a bunch of those on campus. And there are also, for example, large labs that have big accelerator rings to create synchrotron X-ray beams, which are very high energy and also can be focused to very small dimensions and can enable things like spatial mapping of material. So that's a picture of Cornell synchrotron where you have, I guess this is probably a kilometer or so in diameter ring that's used to create the beam, and then the beam is sort of is harvested off and fed to the different labs that have stations like this where you can walk into a leaded room and you can put your sample on a stage and you can take an image down the way. And so this is a picture of a typical X-ray characterization beamline where you put your sample on the stage and the beam comes in here, and the sample in this case can sit in atmosphere, but you want to minimize the amount of atmosphere that the sample is exposed to, and therefore you have vacuum tubes between the input of the beam and your sample and between the output and the detector. And as you can imagine, the distance, the size of the detector, and the distance that you place the detector from your sample determines the angles that you collect. So if my detector is, say, yay big and way out here, I'm going to collect a certain scattering angle. If it's way up here, then I'm going to collect a wider set of scattering angles, and that's based on the configuration and the information that you want to detect. And there are a couple of, you should say, the most useful or simple relationship that's used to get structural information from X-rays is what's called Bragg's law, and Bragg's law relates the scattering angle of the X-rays. So basically how far the X-ray that hits your material is spread out in real space to the lattice spacing of it. And it states that the wavelength of the X-rays lambda is related to the distance d, or the lattice spacing of a material, by the sine of the scattering angle theta. That says that, because lambda is fixed for your X-ray beam, if you have a larger scattering angle, you have smaller features. And so that says that that generally larger scattering angles are used to look at smaller dimensions, and smaller scattering angles are used to look at larger dimensions. In practice, that means that if you had a plot like this, and another way that X-ray data is typically laid out is they typically use an axis called Q, where Q is defined as the scattering vector, which is just an inverse length scale related to the distance d by 1 over 2 pi. If you have the position of your peak here, you could relate this position, this peak, to the lattice spacing d, and if your peak is at higher Q, it means you have a smaller spacing. And if the peak is at lower Q, you have a larger spacing. And if, for example, this is a carbon nanotube and you're using this technique to measure its diameter, which is possible, for example, if you had a whole bunch of nanotubes, then if you see a peak at a higher Q, it means the diameter is smaller. And if you see a peak at a lower Q, it means the diameter is larger. So this is a way purely based on the understanding of the interactions between the beam and the material to measure the size. And in terminology, you can typically measure features using X-ray scattering or diffraction from the lattice spacing or smaller, using wide angles, up to the sizes of typical nanostructures, which are, you could say, 1s to 10s of nanometers. And I'll try to summarize this and pick up on a bit more at the beginning of the next lecture, and then there'll probably be a few things that I'll just leave in the lecture notes for you to catch up on your own, and I'll try to introduce those the first time we talk about them in future lectures. So that's all. Feel free to come up with questions, and I'll see you all on Wednesday.